This is the pre-calculus lesson for section 7.1, day 2, and we had talked about our objectives, which we had already gone through our using substitution to solve systems, graphically solving the systems, and using elimination, but we really had not applied ourselves towards the last objective, which is apply systems of equations to model and solve real-world applications. So we finished up example 6, and that was just, we used elimination to find out that there were infinitely many solutions, because we had talked about what you see up above here, which is you can get a solution, and it would just be one solution if the two lines hit each other, but they might be parallel, so you might obtain no solution. And if the line, in fact, happens to be exactly the same line and it would constantly be hitting itself, that would be infinitely many solutions. But in real life, what we often just want is to know where do the two lines that we have, where do they intersect? So our application here says that table 7.1 shows the personal consumption expenditures in billions of dollars for dentists and health insurance in the United States for several years. So we have the years from 2001 to 2007, and then we see the billions of dollars expenditures here that we have for the dentistry, and then health insurance in billions of dollars. And example 7 down here says that what we're going to do is estimate those personal expenditures with linear models. So A is find linear regression equations for the U.S. personal consumption expenditures for dentists and health insurance in table 7.1, and then superimpose their graphs on a scatter plot of the data. So the first thing I want you to do is to go ahead and enter that data in. But what we're going to do is we're going to use a 0 year. Now, and we don't have huge numbers here, so it wouldn't take us forever to punch this in. But instead of 2001 and 2002, let's just use 1, 2, 3, 4, 5, 6, and 7. And if you remember how to get those in, you can go ahead and pause the video now and put those numbers in. And where we want all of this is underneath stats. And we want to edit, so that would be number 1. And then you'll notice for list 1, I just went ahead and put in our year data, and this would be years since 2000 of 1, 2, 3, 4, 5, 6, 7. And then list 2 entered in the dentistry numbers, and then list 3 would be the health insurance numbers. So we have all of that in there. Now, it had said find linear regression equations, and in the last sentence to part A, it says superimpose their graphs on a scatter plot of the data. So we want to see that data in a scatter plot. And what we would do, and again, you can pause this video at any time if it takes you longer to get the numbers in, whatever, go ahead and pause it. But what we're going to do is second stat plot, so second y equals, and we're going to turn those stat plots on. So while we see the cursor going black and then transparent over the word on, that's what we want to do. We want to hit enter, and it is on a scatter plot, and I will just use the first list, which was the years since 2000, and the second, which was the dentistry numbers the first time around. So I'm just going to go ahead and hit enter on that. But I also need a second stat plot. So second y equals, I'm going to go down into the second one, and I'm going to turn that one on. But notice this time, this is going to use list 1 and list 3. And that's because I want to see the years along with the health insurance numbers, and those would be list 1 and list 3. All the way down and hit enter. So now, what we have to do is set our window so we're able to see these. And our years went from 2001 to 2007. And so I initially just started by saying, you know what, I'll just put -1 to 10 because that'll cover all of the numbers that we have for years. And then when I got to the y min, we might as well start with 0 billions of dollars for dentistry and health insurance. And then I just wanted to pick a number that was higher than any of the numbers that we had, whether or not it was for dentists or health insurance. And since the highest number was 153.2, I just went with 175. So now if I hit graph, I can see the red and the blue here, and those are the scatter plots of the dentistry and the health insurance data. And the dentistry ones started off lower. This was our 1 and 66.8. So here's our dentistry and here's our health insurance. And now what we want to do is we want to find the linear regression for these. And that's going to be under stats. And then we're going to go to calculate. So arrow to the right once. And then we want number 4. Now the first time around, I'm going to have it use list 1 and list 2. So I have to change this by hitting second number 2 to get list 2. And I want this to store it so that I can see that really nice graph for my line over the top of my stat plots. And that comes from variables right here, VARS, and Y variables, so to the right once, number 1 for functions, and then I'm going to choose number 1 for this first linear regression, and then hit enter down to calculate. Now the good thing about this is once we have that in, we could just go to Y equals, and it already put all the decimals and everything in there for us, which is fantastic. Then when you go back, we can do the other linear regression. So stats, calculate, and again it's linear regression number 4. But this time I want it to use my list 1 of my years and my health insurance data, which was under list 3. So that's second number 3. And I don't want to store it over the top of the other one, so I'll do variables, Y variables number 1, but now I'm going to pick number 2. So that will store that in Y sub 2 and calculate. So in my Y equals, both of these are put in, and that will help me do my linear regression. Now, when you saw this before, hopefully you saw the R squared and the R, so let me just go ahead and recalculate one of these to show you that. This was my list 1 and list 3, which I stored under Y variables for functions number 2 and calculated. And remember, the R squared and the R are not going to automatically show up, especially if you've had to clear your memory on your calculator. That's something that you have to turn on again, and those were called diagnostics. So if you really want those, because this R value, the closer it is to 1 or -1, tells us how good a line of best fit it is, then you're going to have to do second 0, which is catalog, and then you're going to just scroll down until you get to diagnostics on. And then you're going to have to hit enter twice. Now, I know on this model, this seems to take forever, but I think it's important that everybody remembers where those diagnostics are so you can get those turned back on. Because if we had to clear them for the MCAs or the ACTs, part of that is that the diagnostics get turned off when we do that. So we keep scrolling until we get to the D's, which, like I said, can take quite some time. And we're looking for diagnostics on. And there it is. So we want to hit enter not just once, but twice, because remember on this main screen, the calculator is waiting for us to hit enter so it will execute what we told it to do. So now if you go back and do those linear regressions with the R values, you'll see that they're pretty good lines of best fit. They're not perfect, but they're pretty good. And the other way to see that is by hitting graph. And we have a nice blue line that goes through those points, and then a red one, which, you know, it's not quite as good as the blue one. We can see that there's some points that are not as close to the line, or we don't actually think that the line is going through those points. So now, this was what they wanted us to do, find the linear regression equations, and then we're supposed to superimpose those graphs on a scatter plot of the data. So for this problem, what we would want to do is go ahead and make a little sketch of what we see here, and then we could go into either the Y equals or do the regression again and write these down, but we only need 3 decimal places. So for our first line of regression, which would have been for the dental information, it would be 4.829x plus, and if we just scroll over on this calculator, it's different for every calculator, then what we would have to do and let me keep using this arrow here, is notice, hey, this one is done at 61.5. There isn't anything else that goes over there, and that's okay. So we just write down our y equals 4.829x plus 61.5. And then the one below it, again, we'll start at the beginning with our 3 decimal places, so 11.432x, and then you just continue to scroll over. And this one is a little slow here. There we go. So plus 78.486. And that's what we'll write down for our answer to part A. So let me get this up here and we'll write that down. And then the second part of this inevitably will be, where do we find the intersection? So scrolling this up a little. For the dentist, y equals 4.829 x plus 61.5. And for the healthcare, y equals 11.432x plus 78.486. So there are the two equations for our linear regression. And of course in B it says use those models to estimate when the U.S. personal consumption expenditures for dentists was the same as that of for healthcare and the corresponding amount. So what we're going to do is go back to the calculator. And when we hit graph before, we weren't seeing that intersection. Pretty obviously that intersection is actually in this direction. That means it was before our 2001, which was our first year. So what we'll need to do is change our window here. We need a few negative x's, so maybe we'll go a negative 10 years and then try and graph it again. And we're hoping to see the red and the blue intersect. And we do. So what we'll have to do next is get Blinky working here. So second, trace, and then we need number 5, intersect, and enter 3 times. And it tells us we have a negative 2.572 years, and that it's going to be at approximately $49.080 billion. So what we want to do is back this up and say, all right, well, we had used 0 for 2000. And what we just found out was that we have to back that up a negative 2.572 years. So if we take 2000 and we subtract that 2.572 years, we get 1997.428. So sometime during 1997, they will be approximately 49.080 billion. Dollars. So that would be our answer. So if we want to know when they would be the same, it will be sometime during 1997, and it will be at approximately $49.080 billion. Then, on the next page, we have supply and demand curves. And supply is what companies are willing to put out at any given time for people to buy. And then the demand is what are we willing to buy. So supply and demand curve, suppliers will increase production X if they can get a higher price P for their product. As one variable increases, the other also increases. So when we see the quantity down here of X, and what they're willing to supply, well, as they increase the quantity, that price is going up. So that's going to be the supply curve. But now that's not what happens for you and me who are the demand and who are trying to buy these. Consumers' demand X for a product will decrease as the price goes up. So as one variable increases, the other decreases. And that is our red demand curve here. As the price is going down, we want to purchase more of these. And so what happens is there becomes a point where your expectations and the supplier's expectations are the same. And that's going to be called the equilibrium point. And that's the point where the supply curve and the demand curve intersect. And this is not showing the whole piece here. That corresponding price is also called the equilibrium price. When you are the supplier, that's the price that you shoot for because you know that demand and supply are going to be equal at that spot. So down below it says determining that equilibrium price, which I'm going to make a little bigger now so this shows up a little nicer. Nibok Manufacturing has determined that production and price of a new tennis shoe should be geared to the equilibrium point for this system of equations. P equals 160 minus 5x is your demand curve, and then P equals 35 plus 20x is a supply curve. The price P is in dollars, and the number of shoes X is in millions of pairs. Now, that's important because we're going to need some labels lately, later when we get going on this. So it says find the equilibrium point, and they want us to use substitution to solve the system, which is great because that's going to happen really easily. Because if 160 minus 5x equals P and 35 plus 20x equals P, well, then they have to equal each other because they both equal the price. So 160 minus 5x is going to have to equal 35 plus 20x, and we can just solve this and we will be able to find x, which is the millions of pairs of shoes. So if we add 5x to both sides and subtract 35 from both sides and divide by 25, we will get 5. So that means they need to produce 5 million pairs of tennis shoes. Now, the part the business is going to care about here is price. What does that mean as far as the price goes? So what we have to do is take our x equals 5 and plug it back into either one of these two equations so that we can figure out what the price would be. So the price will equal 35 plus 20 times 5, which 20 times 5 is pretty obviously 100. So it will be $135 a pair. So there's the equilibrium price. If they charge $135 a pair, they should be able to sell 5 million pairs of tennis shoes. So that one was pretty basic. It takes a long time to get everything into the calculator for those that we have to do linear regression. But these work through it really nicely. So our objective of applying systems of equations to model and solve real-world applications has been met with those last two problems. And again, those are the two assignments. I would like you to notice here that for number 46 in the second day here, we don't want you to find when one is more than another one. We want you to find when they're equal so that you're doing that equilibrium price. So you should be able to get through both of these now. And we'll be back at it on Thursday.